Welcome to qubit-lab.ch. In this video, we look at how quantum generative modeling might help with a very practical finance problem, generating joint stress scenarios for credit tail risk. More specifically, we combine empirical copulas with a quantum circuit-borne machine, or QCBM, to model joint spread widening behavior across BBB, BB, and broad high-yield credit. Let's start from the business problem before we go into copulas or quantum circuits. I will first frame the credit risk use case, then show why a copula is a natural way to model joint tail dependence, and finally explain how a QCBM can learn that dependence structure and generate new scenarios. After that, I will walk through a concrete notebook example and the main results. So what is the actual risk management problem we are trying to solve? A credit risk engine needs many joint scenarios to estimate tail-sensitive quantities such as value at risk, conditional value at risk, or CVAR. But extreme co-movements of BBB, BB, and high-yield spreads are rare by definition, so the empirical tail is sparse. Many relevant joint bins contain very little data or no data at all. The idea here is to train a QCBM on the observed joint spread behavior and then use it as a scenario generator. If that works, we can produce many additional joint samples that remain consistent with the learned dependence structure and feed them into an existing risk tool. Let's make that business setting a bit more concrete. Suppose a portfolio manager holds a diversified credit portfolio across 3 rating buckets: BBB, BB, and broad high yield. In normal times, that looks sensibly diversified. But under stress, these segments can widen together, and diversification can break down exactly when it matters most. So, the business question becomes, what is the probability of a joint spread blowout across these 3 segments, and how large could the resulting mark-to-market loss be? That matters for risk limits, stress testing, capital buffers, hedging, and de-risking decisions. And just to ground the terminology, we observe corporate credit risk here through credit spreads, meaning the extra yield demanded over a government benchmark such as treasuries. Higher spreads generally mean higher perceived credit risk. Now that the use case is clear, we need a model for joint tail dependence. In this example, we use 3 spread indices: BBB OAS, BB OAS, and broad high yield OAS. The goal is not just to model each marginal separately, but to capture how these 3 move together, especially in stressed conditions. That is why we construct an empirical copula from the 3 spread series. The copula gives us a dependence model for simultaneous spread widening, which is exactly the object we need for joint tail risk analysis. So what exactly is a copula in this context? A copula models dependence separately from the individual marginal distributions. In our case, BBB, BB, and high yield each keep their own spread move behavior, while the copula captures how their percentiles cluster jointly, especially in the upper tail. Why is that useful? Because correlation mainly captures average co-movement. Tail risk, however, is about joint extremes. Operationally, we take each marginal map observations into percentiles and then study how those percentiles bunch together. Once the copula is discretized into a joint grid, the problem becomes one of representing and sampling a large joint probability distribution. And that is where quantum generative modeling enters the picture. If we discretize a copula on a full grid, the number of joint cells grows exponentially in the number of assets for a fixed bin count. So even though the classical representation is straightforward, it quickly becomes unwieldy as dimensionality increases. A QCBM offers a different angle. Instead of explicitly storing the full joint table, it uses a parameterized quantum circuit as a compact generative model trained on sample data. The important point is not that the difficulty disappears. It won't. Rather, the bottleneck shifts from explicit storage toward model training and validation. So let's make that concrete. What is a QCBM and why is it relevant here? A QCBM, or quantum circuit-borne machine, is a parameterized quantum circuit that defines a probability distribution through the Born rule. Training adjusts the circuit parameters so that the output distribution matches the observed joint sample structure. For our credit example, we use 3 marginals and 8 bins per marginal. That gives 8 to the power of 3 equals 512 joint cells. In principle, a QCBM can represent a distribution over those cells using only n times the 2 log of b qubits, which here means 9 qubits. And once trained, the QCBM can generate as many new samples as we want from the learned distribution. For this use case, repeated measurements directly become new joint spread scenarios. Explicit cell probabilities only matter when we want to inspect or validate what the model has learned. Now let's move from concept to the actual notebook workflow. From here on, I switch from concept to implementation. I will show how the target distribution is built, how the QCBM is trained, and what the results look like for both the full distribution and the stressed tail corner. First, here is the modeling pipeline in one picture. The workflow is simple at a high level. First, we define the target distribution by discretizing the empirical copula grid and counting how often each joint cell is hit. That gives us the distribution the model should learn. Next, we define a trainable ansatz circuit. Its parameters play the role of model weights. We then estimate the model distribution implied by the circuit, compare it with the target distribution using a loss function, and update the parameters classically. Once the parameters are frozen, repeated circuit measurements generate new sampled copula states, which in our setting are new joint credit spread scenarios. So this is distribution learning first, scenario generation second. Let's now look at the actual notebook setup. The data comes from Fred and consists of daily BBB, BB, and high-yield spread indices over the 2000 to 2025 window. The input variable is not the level itself, but daily spread changes. Each marginal is transformed into pseudo-observations via an empirical rank transform, then discretized into 8 bins. With 3 variables, that gives us a 3D copula grid with 512 discrete states. The quantum model is a 9-qubit QCBM in penny lane with a custom ansatz and simulator-based training. For fitting, the notebook uses KL divergence as the training loss. For evaluation, it uses JS divergence and tail cell comparison alongside 20,000 shot scenario sampling and a comparison between a baseline model and a stress, non-stress regime split. With the setup in place, let's go straight to the most important result, the stressed tail corner. Here we compare 3 distributions on the same 8 by 8 by 8 copula grid. First, the empirical distribution directly observed in the data. Second, a baseline QCBM trained on the full empirical copula. Third, a regime mixture QCBM, where separate stress and non-stress QCBMs are recombined using empirical regime weights. The notation IJK denotes 1 copula grid cell for BBB, BB, and high yield. The state 777 is the maximum stress corner. All 3 spread changes land in their highest bin at the same time. This is the key result. The baseline QCBM underestimates the most extreme joint tail state by 18.6%. The regime mixture QCBM nearly matches the empirical tail mass with a deviation of only 0.3%. So the regime split materially improves extreme tail calibration. That was the sharpest tail result. Now let's broaden the view and look at the full distribution. These 3D plots compare the full probability landscape across all copula grid cells. Bubble size and color indicate probability mass. The visual takeaway is that the regime mixture QCBM tracks the empirical distribution more closely than the single baseline QCBM, while still preserving the dominant upper tail corner. In other words, the improvement is not only at one single tail state. It also carries over to the broader joint distribution. So what does that mean in practical risk management terms? Once trained, the QCBM can generate large numbers of synthetic joint spread scenarios that remain consistent with the dependency structure learned from historical data. That matters when extreme joint tail events are too sparse in the raw data. Instead of relying only on a thin empirical tail, we can enrich the scenario set with additional dependency-aware joint stress scenarios. Importantly, this does not replace an existing risk engine. It augments it. The generated scenarios can support workflows such as VAR and CVAR estimation, stress testing, tail risk scenario enrichment, and sensitivity analysis. So in practical terms, the QCBM can act as a dependency-aware scenario generator for tail risk analysis. Before getting carried away, it is worth being explicit about the limits of this proof of concept. This notebook is a simulator-based proof of concept. It uses only 3 marginals and 8 bins per asset, so it is still a small-scale setting. The results are also sensitive to discretization choices, ansatz design, and optimization stability. The regime split helps clearly in this dataset, but it may not always outperform elsewhere, so this is not a universal claim. The next steps are straightforward: more assets, finer grids, out-of-sample validation, alternative circuit designs, and integration into downstream risk workflows. So the right reading is, this notebook shows modeling potential, not yet production readiness. With that caveat in mind, here are the main takeaways. Credit spread tail dependence can be represented on a discretized empirical copula grid. A QCBM can learn that joint distribution and generate new dependency-aware scenarios. In this notebook, the regime mixture QCBM matches the most extreme joint tail state far better than the single baseline QCBM. That makes the approach relevant for tail risk scenario enrichment in downstream VAR, CVAR, and stress testing workflows. At the same time, this remains a simulator-based proof of concept, not yet a production-ready solution. So the broader message is this: quantum generative modeling may become a useful complement to classical tail risk scenario generation once scalability and robustness improve. And if you want to explore the notebook or discuss related use cases, here is where to find me. At qubit-lab.ch, I focus on readiness, enablement, and proof of concept support for organizations developing quantum capability. That includes education, use case discovery, roadmap development, vendor navigation, and POC execution. If this topic is relevant to your organization, feel free to reach out. Have a great day.